All right, in this video, we're going to take a look at the start of section 5.6.1, where we're going to talk about our second to last test, the ratio test. What you'll see right here at the start is that what I have here kind of written out is that we've seen already in previous sections, specifically back in 5.3.1, when we talked about the divergence theorem, the divergence test, is that it must be the case that in order for a series to converge, the limit of that the limit of that inside sequence has to be 0. That was a definite criteria. At the time, we said that that was something that was necessary to happen, but not sufficient. That wasn't the only thing that we needed to happen. Because again, things like the harmonic satisfied this, but also didn't converge. So one of the other conditions that we technically need, one of those other necessary conditions, would be kind of what we have down here. We not only need to have the limit of the a sub n turning into 0, but we kind of need to have that a sub n moving toward 0 at a quick enough pace. Now, in this section, we have a ratio test that we're going to use to kind of help us understand a little bit more about how this quickly enough sort of criteria actually goes. And it works by using this test, or this test at least highlights the use of that idea. Now, as you'll see here, we're not going to be going through the proof of this theorem here today. We're just going to be taking a look at how we can actually implement it. The proof is a little bit complicated. It is in the textbook if you want to go ahead and take a look at it. Well, let's see what we got here. Let's first read the theorem. Let's suppose that we have a series with a sub k. K starts at 1, goes to infinity. And it's going to be a series with non-zero terms. I'm definitely going to need things that are non-zero because I'm going to be setting up a ratio, and I want to make sure my denominator doesn't turn into 0. Now, let's suppose that we set up a limit of a ratio of the k plus 1th item over the kth item, and we take a limit of it as k goes off to infinity. So this is kind of almost similar to like when we did ratios of consecutive terms to show increasing and decreasing, but it's a little bit different now because we have this limit on it, and we're also going to absolute value things on top and bottom. Now, when I do this limit, I'm going to come out with an answer, and we're just going to give that answer a name. You don't have to give it a name, but in this case I do, and I call it this Greek letter rho. So if you've never seen that before, that's R-H-O. It's Greek letter rho. Looks like a P. Okay, and here's what we find. Some cool things start to pop out. If it's the case that rho comes out less than 1, right? I crunch out this big limit, I get a number under 1. Maybe I get like a half. Then I know that the original series converges absolutely. That is, it gets the blue title like we talked about in the last section. And therefore, well, automatically, we said that if something is ever absolutely convergent, that's like super convergent, and that means it should regular converge. So that's pretty nice. If it comes out that this limit comes out to something bigger than 1, maybe I get like a 10, or maybe if it even comes out as a positive infinite, then I get divergent. I get the good old black title. And if it's the case that rho is equal to 1, we get something that really sucks. We get that the test is inconclusive. Essentially, the test tells us nothing, and we're completely stuck. All right, so this isn't fun at all. We hope that we'll never get a 1. But the important thing to keep in mind here is that there is a condition again before I start this test. I need to have non-zero terms. So let's take a look here at example number 1 to quickly kind of work through an example of when the ratio test can be useful. One of the most common points in time when a ratio test is useful is when you start to see series like here in example 1 where there are factorials involved. You might remember that on the skills check we looked at how to simplify factorials, and they were really easy to do as long as they were being like divided. And since a ratio test helps create a division of two things, it's really ideal as something to try to at least use when you come across something with factorials. So here's what I'm going to go ahead and or how I would actually work through this question. I'll start by noting that very, very clearly the series contains only non-zero terms, right? There's no terms coming out of this series that are going to be 0. So I'm going to go ahead and use the ratio test then. So I'll say we compute, and the ratio test says that I should just start by setting up a limit as k goes to infinity. And on the top, I'm going to put absolute value bars around the k plus 1th term. So notice that k plus 1 has to be in parentheses, and then I will put the factorial symbol on it. On the denominator, I'm just going to have my 1 over k factorial in absolute value bars. Now, what's kind of surprising here is that when I set this up, the first thing I'd have to ask is, how do I simplify away the absolute value bars? Or can I simplify them away? But of course, here that's super easy, because does 1 over k plus 1 factorial or 1 over k factorial ever make something that's negative? Well, the answer to that is very clearly no. So those absolute value bars can just be completely removed without any consequence. And once I have that, now I'm going to have the freedom to go ahead and simplify as I would normally do. So I'm going to get something that looks like this when I multiply by the reciprocal. And you could think really quickly about how you simplify out those factorials. Take a moment, pause the video if you need to, and think about how you would simplify down those factorials. Okay, so if I was to simplify those down, I would get something like 1 over k plus 1. And the limit of that should be 0. Now, that value of 0, remember, is exactly what we called the value of rho. So if rho is 0, I recognize that that is under the value of 1. And so that means, and I'll write it here, that therefore, by the ratio test, our series is absolutely convergent and therefore convergent. All right, so that kind of goes ahead and works us all the way through our first example there. In the next video, we'll take a look at a couple other examples to see how exactly we could continue to use this in the way that we might have to be a little more careful with these absolute value bars.